Et donc, ça va être sur le Go avec Felix. Donc, Felix est un employé de Datadog et il nous a rejoint il y a pas longtemps. Et donc, c'est un expert sur Go. Il travaille sur profiling Datadog pour Go. Et puis, donc, il va nous parler de ça. Et après, on pourra, donc dans l'application Wonder, on pourra discuter. Normalement, quand on aura fini le broadcasting, on pourra discuter soit un gros groupe en cercle, discuter directement avec le speaker pour lui poser des questions, ou si vous retrouvez des amis parmi les avatars, vous pouvez aussi créer vos groupes et avoir des discussions plus privées si vous le souhaitez. Donc voilà, c'est un essai, on va voir ce que ça donne. J'espère que le mois prochain en physique, ça se passera mieux. Mais voilà. I will switch in English now and introduce Felix to start his presentation about Go. Felix, if you want to start, I'll let you the mic for starting your presentation and sharing your slides. We can see your slides, but we don't hear you. Petit problème technique avec Felix, forcément. Voilà, ça va bientôt revenir, je pense. Il essaie de se reconnecter.
On avait bien son micro tout à l'heure. Hein. Ça avait marché. On avait bien le micro de Félix tout à l'heure.
Bah ouais, ça marche bien.
Parlé, hein. Okay.
Ouais. Si je fais. Hey Felix.
Oh, hi Felix.
Hey, is it working?
Okay.
Yeah, it is. Great.
All right,
Good.
I had to reload. And
okay.
Computers. Sorry. Let me
No
share
problem.
my screen again.
Okay. In the meantime, si vous avez des questions, vous pouvez les poser dans le chat everyone. Je les poserai à Félix si besoin est directement. So if there is question in the chat, I'll try to so Felix will try to monitor the questions, but if there is a question that I can ask directly, I will join into the broadcast to ask you. So when you want.
All right, let's get started. I unfortunately don't know a lot of French, so thank you all for listening in English. But I can say merci beaucoup to Jean-Philippe for the introduction. And yeah, welcome to my presentation, Continuous Go Profiling and Observability. The target audience for this presentation are Go developers and operators of Go applications. Basically anybody who's interested in reducing cost and latency or debugging problems. As in, you want to make your applications written in Go run better. I think this presentation could be interesting. The focus is going to be mostly on Go's built-in profiling and performance tools, but we'll also talk a little bit about Linux Perf and eBPF, since those are interesting tools in that space as well. About myself, my name is Felix Geisendörfer, and as said in the introduction, I'm staff engineer at Datadog, working on continuous Go profiling as a product. Before joining Datadog, I spent 6.5 years working for Apple, where I was working on factory traceability stuff using PostgreSQL and Go. And over the years, I've also always been a very active open source contributor. I was one of the first core contributors to Node.js, wrote a lot of NPM modules, I have written a lot of Go modules and contributed a little bit to Go itself as well. And if any of that is interesting to you, you can check out my GitHub README, which is a good list of projects. The slides for this presentation you can find by scanning this QR code or visiting this link. At this point, apologies for reusing this slide deck from a previous conference where I've given this presentation. The previous one, however, was recorded. This one is live. So the benefit here today is I'll go into a little bit more detail. And also, if you have questions, you can ask them during the presentation and we can kind of go off topic a little bit, depending on what people are interested in. I'm really happy to speak about anything Go performance profiling related that you want to hear about. So let's get started very basically. What is profiling? To me, profiling is anything that produces a weighted list of stack traces. The most common example of such a tool is a CPU profiler. And usually those work by interrupting a process for every 10 milliseconds of CPU time that a thread spends running on the CPU. And then the thread is briefly stopped, a stack trace is captured, and then a table like shown below is produced that basically is a frequency table of stack traces where you have the stack trace in the left column and then the number of times that particular stack trace has been seen in the right column. And that's what we generally call a profile. You can visualize those in flame graphs and all kinds of other stuff, which we're not talking about today, but we're talking a little bit more about where this data is coming from and how to get it in Go. Then continuous profiling, which we're also talking about a little bit, is the idea of profiling in production. And what that means is basically just running a profiler in the background while your application is running, and then uploading those profiles that are produced by the profiler to a backend for later analysis. So you always have profiling data available, and you don't need to SSH into machine or do some stuff to get profiles. One question that obviously comes up there is, why would you want to profile in production? The answers to that, from my point of view, is that data distributions can have a very large impact on performance. So it really matters what the workload looks like. And it's often very, very difficult to simulate realistic workloads in a local development environment or in a testing environment on some servers. So if you want the real data about how your application is performing and where your bottlenecks are, production is pretty much the only place you can get it. The other thing that I find quite interesting is that production profiles can help with mitigating and root causing incidents. A little personal story from my last job at Apple. We were running Postgres, which is not written in Go, but you can profile Postgres using Linux Perf. And one day we had a problem with a Postgres instance that was stuck in a vacuum and wouldn't progress. And we unfortunately only noticed once we got a wraparound issue which took down the database, which is very bad. And so we were trying to figure out what's wrong with the database. And the CPU profile gave us a valid or a really good hint. What we saw in the CPU profile was that the vacuum process was essentially spinning in a loop that was navigating the B tree nodes of a index that we had. And with that clue, we were able to eventually identify which index was being impacted. And we determined that it was a index corruption. We still don't know if it was a bug in Postgres or a bit flip or something weird, but or the storage layer. Yeah. Anyway, the end result was we were able to figure out what the root cause was, and we were able to then mitigate it by deleting the index that was giving us problems, recreating it, and that brought our database back online. And so stuff like this, profiling can be really good for. Maybe more commonly, you'll see functions that usually don't take up a lot of time suddenly taking up a lot of time, or stuff that usually doesn't allocate much suddenly starting to allocate a lot of memory. And that gives you a clue that maybe your workload has changed, maybe you're under attack. Stuff like this you can get from profiles. And yeah, the last reason for profiling in production is, why not? It's very low overhead. Most profiling tools that we're going to talk about today have an overhead of 1 to 10%, usually closer to 1%. And unless you're running a very, very, very performance cost sensitive application, profiling pays for itself very quickly. The improvements you can make far exceeds the overhead that it's introducing. So hopefully it's a no-brainer from that perspective for most people. All right. Now let's talk about Go. Go is a compiled language like C, C++, and Rust. And for a lot of people, that means that they automatically assume that it should work well with industry standard observability tools, and that you should be able to just take any tool that works for C, C++ or Rust application and use it with Go and get good data. So in order to determine if that's true, we're going to put Go through the duck test. The duck test is if it looks like a duck, swims like a duck, and quacks like a duck, then it's probably a duck. And the question here, of course, is Go a duck like other compiled languages? So let's find out. So the first thing to know about Go is that it's operating using green threads called Go routines that are scheduled onto operating system threads by the Go routine. These green threads are tightly integrated with Go's networking stack using stuff like ePortal on Linux. So if a Go routine is waiting on networking, Go is automatically able to deschedule it and run another Go routine on the thread, which is very nice. Actually, kind of similar to Node.js and how the event loop is implemented there. Go is also optimizing these green threads, these Go routines, by using very small stacks. Typically 2 kilobyte is the stack size of a Go routine. And then one thing that's kind of unusual is that the Go routine stacks are grown dynamically. So if you're running a Go routine that uses more than 2 kilobytes of stack space, instead of getting a Stack Overflow error, you actually get a bigger stack and you don't have to even think about it. It's all happening in the background. And all of this above leads to really good performance characteristics, especially when it comes to switching between Go routines on the Go routine scheduler side, which is much faster than Linux, the Linux kernel's ability to schedule Linux threads. And it's roughly 10 times faster. So maybe 170 nanoseconds to switch from one Go routine to another, which is very, very good. Last but not least, data sharing between Go routines is accomplished using traditional mutexes, but Go also has a feature called channels, which is a implementation of communicating sequential processes invented by Tony Hoare. So now that we've discovered how great Go routines are, let's figure out how much of a pain in the explicit word they are when you try to use observability tools that are not aware of Go routines and what they're doing. What we've got here is a BPF tray script. We don't need to talk about all the details, but what it's basically doing is it's instrumenting, it's putting a uprobe on our example binaries main.foo function. And then it's also putting a uReturn probe on the same function. And what this would allow it to do is to measure the latency of this function in wall clock time. So when that function is called, we start a timer. When it's stopped, we measure the time that has elapsed. Now, with most C, C++, and Rust applications, this works great and is super useful. But if you do this with Go, you will quickly discover that uReturn probes and dynamic stacks are not really friends because of the way that uReturn probes are implemented by manipulating return addresses on the stack. And that's not very good if the stack is dynamic and is being moved around in memory. And that can lead to crashes like the one you're seeing here. There are workarounds for this, but there are all kinds of tricky and error prone. For example, you can put uprobes on all the return instructions, but that doesn't deal with panics and so on. So anyway, the other thing that even if you figure out how to make uReturn probes work correctly, you've got another problem. This script was using the thread ID as the identifier for keeping track of our timings, but in Go, that doesn't make sense. We really need to get the Go routine ID. And getting a Go routine ID from the Go runtime is very, very tricky. You have to basically know internal data structures of the scheduler to be able to get them out. Here's some code that could do that, but don't use that in production, please. So the reason why I'm showing this is just to highlight the fact that Go routines are fantastic, but if you try to throw some tools at them that are not aware of them, it can lead to bad things happening. So be aware of that. The other thing that Go is kind of unique in Go is that Go doesn't follow the systemd AMD64 ABI, which is the calling convention of how function calls are invoked on the machine code level. Prior to the latest release of Go, which is 1.17, it was totally different than most or most programming languages, Go was actually passing all the arguments on the stack rather than using registers, which was inherited from Plan 9. And that's kind of slow. Luckily, Go 1.17 has decided to switch to a register-based calling convention that looks a lot like what C and C++ are doing, but it's still idiosyncratic, using different registers. And the reasons for doing that is to A, support Go routine scalability, and B, to support multiple return arguments. So that can still confuse some tools. Some tools are fine depending on how well they make use of 12 debugging information and stuff. Also worth knowing, even so now Go looks a little bit more like C and C++ in this regard, it still actually supports the old calling convention using stack passed arguments underneath, because any code that was written in Go's assembly language is still being invoked with a function call that's actually putting the arguments on the stack rather than using registers, because otherwise those assembly functions would break because they don't know where to find their arguments. So you essentially have to deal with two calling conventions in Go applications now, and none of them are actually the default conventions you would expect elsewhere. So that's fun. And last but not least, calling C code from Go is, as a result of all the previous stuff, also kind of tricky. Basically, to call C code, you have to have a separate stack where you put the C call frames on, because everything in C assumes that stacks are static and don't grow dynamically. So if you try to put C frame information on a Go stack, that would end up with very bad things. And the end result is that when Go wants to actually call the C function, it has to switch from the Go routine stack to a C stack, which has some complexity and a little bit of overhead. It's usually fine if you make a function call that does some significant work, but if you have a very tiny function that you want to invoke that might be executing less than 60 nanoseconds, the overhead of 60 nanoseconds is pretty high for a call here. A few things, however, are less odd about Go. Specifically, stack traces is one of them. So Go implements frame pointers, which means there is information on the stack that allows an external tool to actually unwind the stack and get a stack trace. And unlike C, C++, and Rust, there is no compiler option like formit frame pointer, which would remove those. So usually Go binaries are in a much better place to be profiled and debugged from that point of view when you need a stack trace. Another thing that's super nice about Go is that it always generates 12 unwind and symbol tables. So you always have debugging symbols in Go applications, and you kind of need to go out of your way to get rid of them. Whereas in those other languages, it might be the other way around, which is not great if you deployed something in production and then realized you would like debugging symbols to make sense out of crashes and other stuff. Last but not least, or not even last yet, this stack trace infrastructure in Go, the frame pointers, leads to good interoperability with tools such as Linux Perf. Linux Perf can do frame pointer unwinding, and it can use 12 to symbolize stuff. And so out of the box, Linux Perf and Go get along pretty well. The Go runtime, however, doesn't use the frame pointers that I just mentioned. The Go runtime uses a idiosyncratic Go PC line tab implementation of asynchronous unwinding and symbol tables, which is basically a lot like 12, but specifically tailor-made for the Go runtime. And one of the reasons why that makes some technical sense and is not entirely crazy is that 12 information is strippable, and Go really needs this information in some cases. For example, to execute a panic, it needs both the unwinding information as well as the symbol information. And then the other really good reason is that 12 is really an insane kind of debugging standard. To get an idea of how insane it is, 12 is actually Turing complete. So if you get a stack trace using 12, the unwinding of the stack trace is executing bytecode that is implemented or integrated into the debugging section of your binary in a virtual machine, which is very, very complex for something that should be simple, like getting a stack trace. Famously, the Linux kernel did not allow 12 to be used for unwinding in the Linux kernel because it was deemed just too crazy and out there in terms of complexity. But it's used in industry a lot, so it clearly seems to work well for a lot of people. That basically concludes our duck test. I think it's fair to say that Go kind of looks like a duck, but it's definitely an odd duck, where you can assume some stuff to kind of work out of the box, especially Linux Perf. But for some other stuff, you should always be careful when using third-party tools and bring a little bit of understanding to what those tools are doing and whether or not that, in the worst case, might even crash your Go application. So the safer path is to stick with the built-in tools, which we'll come to shortly. So given all these bad things, why would you even bother with Go if you have the choice? Because for a lot of people, the Go language has a quirky runtime, as we just discovered. It's a pedestrian language with a very limited type system. But to me, there's still some charm about Go. And the main thing for me is that what Go lacks as a language, it makes up for in tooling. Go has really a lot of good tooling built in by default, which is very easy to use. And it includes documentation tooling, testing, benchmarking, code formatting, execution tracing, profiling, and much, much, much more stuff. And that usually means you can be quite productive and get interesting programs written in Go that might be more difficult to write in other languages with relatively good performance as well. Talking about the built-in observability tools, Go ships with 5 different profilers: a CPU profiler, a Heap profiler, a Mutex profiler, a PerfUG profiler, and a Go routine profiler. And as I mentioned, it's all built in. So for example, if you have a benchmark and you want to get a CPU profile and a memory profile, you just have to pass some flags to Go test, and off you go, and you've got the profiles you want. And Go also ships with the pprof visualization and analysis tool, which can produce flame graphs, like shown below here, as well as these GraphViz visualizations. And all you need to do is invoke Go tool pprof, and off you go, and you get a visualization of your profiling data, which is really nice to have built in. Another tool that's built into Go is the runtime execution tracer. This one basically records everything the runtime is doing, including every decision made by the scheduler. So whenever a Go routine gets scheduled onto an operating system thread or descheduled, you get a record for that in the execution trace. And just like the profiling tools, you can actually look at those execution traces using the built-in tools. So you can actually get a visualization like the one I'm showing here in the screenshot below. We're not going to talk about this too much today. The main warning here is that the overhead of the execution tracer can be a bit higher because it produces a lot of data, and you cannot select which data you want and which data you don't want. So it's an all or nothing thing. Now let's talk a little bit more about the built-in profilers. There are 3 profilers in Go that measure time: the CPU profiler, the PerfUG profiler, and the Mutex profiler. They actually measure different kinds of time domains. So the Go routine scheduler is basically responsible for moving Go routines between the executing state in this red box here into the waiting state when they're waiting on networking or channel operations or other stuff when they're not actually running on the CPU. This is off CPU on the bottom right. And then there's a runnable state, which is a queue for Go routines that want to execute on the CPU, but all the CPUs are currently busy. And so the CPU profiler measures the amount of time Go routines are spending while they're on the CPU assigned to a CPU core, or more specifically, an operating system thread. The CPU profiler also has a very cool feature that is not common in other profilers called profiler labels. And what they allow you to do is to basically annotate Go routines with arbitrary key value pairs. So above in this little code snippet here, you can see that we're creating a set of labels with a user ID and the value. And then we're executing some code with those labels applied. And now the profiler, or the CPU profiler specifically, when it creates a profile, will not only record the stack traces, it will also record the labels associated with the Go routine. And even better, when you start a new Go routine with a Go statement, those labels will be inherited by the child Go routines automatically, so you don't even have to do anything. And so that is really powerful feature. You can use it to basically understand CPU consumption broken down on the level of individual requests, users, endpoints, whatever you want really. You can put anything there. Now some implementation details of how this actually works. So the CPU profile on Go is, oh, actually, this is slightly outdated now. In the latest released version of Go, which is 1.17, Go uses the set itimer system call, which basically asks the operating system to send a sigprof signal for every 10 milliseconds of CPU time that a thread spends running on the CPU. And when such a signal is received by the Go runtime, the signal handler takes a stack trace and then essentially aggregates it into the CPU profile. And the problem with the set itimer API is that it has some thread delivery bias, and it can't really keep up when utilizing more than 2.5 cores. So you don't get enough sigprof signals successfully delivered to the Go runtime. And that can be a little issue if you have a spiky workload where you might underestimate the code that's running when your CPU load is spiking, which is not great. So Reese Hiltner and myself, Reese is at Twitch, we were working on a patch to get this fixed upstream. And the good news is that this patch has been merged and is probably going to show up in the Go 1.18 release. I should say that it's pretty much all Reese work. I was supporting testing and discussions, and my tests didn't end up getting merged so far. But his patch is now using the timer create API. And for various reasons, this API does not suffer the same issues when it comes to keeping up with the signal delivery rates that itimer is suffering from. Now the next profilers are the Mutex and Block Profiler. As I mentioned, those are in a slightly different time domain. So this is not CPU time, this is Go routine time. So if you were to start a timer in a Go routine, that's the time domain we're talking about. And those two profiles are similar enough that I'm going to cover them together in one slide here. Basically, what they do is the Mutex Profiler shows you how much time Go routines spend off of the CPU while waiting for mutexes. And the Block Profiler shows you also mutex waits, but in addition to that, also channel waits. So if you're waiting to receive a message from a channel or send a message to a channel that might currently be full, the Go routine gets descheduled from the CPU and woken up again when the message can pass through the channel. And that time duration shows up in those profiles. One question that some people might have is, given that the Block Profiler is capturing both mutex operations as well as channel operations, why wouldn't you just always use the Block Profiler, which covers both, instead of the Mutex Profiler? And the answer to that question is that the Block Profiler captures the site of the lock operation. So it captures how much time is waiting to acquire a lock. Whereas the Mutex Profiler captures the unlock, which is basically tracking the amount of time that was spent by the Go routine that gets scheduled onto the CPU after unlock, or sorry, that manages to get the lock after unlock calls. And another way to say that might make more sense is the Block Profiler shows you the locations in your code that have to wait because they cannot currently acquire lock. So that's where the contended Go routines are. And the Mutex Profiler shows you which locks are actually causing that contention. So who's holding the lock that is causing other people to have to wait. And so both of these perspectives can be super useful. The Block Profiler also used to have an issue, which I discovered while reviewing the code for it. And it used to be a little biased. And this has been fixed in Go.1.17 through a patch I was able to upstream. To recap the profilers, there are, again, 3 profilers measuring time. There is a CPU profiler, the Mutex, and the Block profiler. And they all sort of measure Go routine time, but the CPU profiler measures the subset of Go routine time that a Go routine spends executing on the CPU, while the Block and Mutex profilers measure Go routine time off CPU, waiting for mutexes and channels. And then, as you can see in this graph, there's still some surface in this Venn diagram in orange that is not actually captured by any of the profilers. And perhaps the most important one is networking. So if you are waiting on IO assist calls like read and write, then that does not show up in any of the profilers currently. And the answer to detecting problems around that is usually distributed tracing, where you manually instrument your code paths to figure out how much time you wait on network requests and stuff like that. Then we are leaving the area of time-based profilers and we get to the memory profilers in Go. Go has a allocation and heap profiler, which basically keeps track of A, how many allocations are we doing, and B, which of these allocations are still on the heap. And what I'm showing here is essentially how that is implemented. So through some pseudocode. Let me see if I can get my laser pointer going here. Yeah. So we got the malloc function here, which is basically called every time you allocate memory in Go, which then does some magic to allocate the object. Then it checks, it uses a Poisson sampling algorithm to decide if a given allocation of a given size should get sampled, because it's a sampling profiler. If you were to sample all the allocations made by the Go program, the overhead would be too high, it would be too slow. But if that particular sample is chosen, and the default is one sample every 512 kilobytes of allocations, then a stack trace is taken. And then there is a global hash map that uses the stack trace as a key. And in this hash map, we increment the number of allocations, which is a counter, and we increment the amount of bytes that have been allocated. And last but not least, in malloc, there is a little flag set on objects that are being sampled for memory profiling, which basically associates the object with the stack trace that created it, which is then used by the sweep function. So sweep is being invoked when the garbage collector cleans up some memory. And what it does is it checks if the object is a profiled object, which is detected by the presence of an associated stack trace that was used to create it. That stack trace you can then get out of the object or some other place in the memory management system of Go. And now in the profile, we can also increment another counter with that stack trace, which basically tells us of all the allocations that happened at the stack trace, how many of them have been freed already, and also how many bytes have been freed. And we'll come back to these counters in a second. But yeah, basically we end up with allocations per stack trace. And the other thing that we get reported as users is then the memory that's remaining in use on the heap. And the way that the Go runtime can tell us that in the memory profile, so basically subtract these allocation counters from those free counters that we've seen before. The frees themselves are not reported in user-facing profiling information. And what you can do with this is basically identify the source of memory leaks. Like you can look at the in-use memory profile and see where the data that you suspect to be leaking was allocated. What you can't really do with that is figure out what is currently still referencing this data, as in why doesn't it get garbage collected. Hopefully that's something where Go's tooling will evolve in the future, but for now you can really only get the source of potential memory leaks. A few surprising things about the allocation and heap profiler is that sometimes the memory profilers can guide CPU optimizations better than the CPU profiler. Because it's very common for Go applications that spend up to 30% of their time on activities related to memory management. So if you, instead of looking at your CPU profile, which memory management activities will often show up as death by 1,000 paper cuts, because you got the allocation costs somewhere in the flame graphs where the user code is running, then you got the GC kind of separate. It's kind of hard to see where you should go. But if you use the allocation profiler, and you aggressively optimize away allocations, that can really give you back a lot of CPU time. Perhaps an even more interesting way it gives you back CPU time is second order effects. Because if you reduce allocations in one part of your code base, it can actually make other parts of your code run faster, because you essentially end up needing less memory, and you can keep more of the stuff that you care about in the hot CPU caches, and that makes other code run faster because you have less memory stretching. So one way Brian Boreham put it on Twitter is if you can remove 10% of GC work, your program will run 30% faster. Now, whether or not that's true for your particular workload, you'll have to test. Your mileage might vary, but it's a surprising and super useful thing to know when you decide where you should go to make your stuff run faster, specifically if you have a lot of CPU usage and also allocation usage. Another tip on that is that when you think about optimizing for allocations, one thing to keep in mind is not just to reduce the number of allocations, but also reduce the number of pointers to those allocations, because the GC will essentially have to iterate over all of those pointers in order to see what's still referenced. So even if you have a low number of allocations and high number of pointers to them can still be problematic. All right, that gets us to the last profiler, which is the Go routine profiler. The Go routine profiler is very different. What it essentially does is it briefly stops all the Go routines that are currently running and captures a stack trace from them. This is useful for debugging stuff like Go routine leaks. That's actually one of the interesting ways you can have a memory leak in Go, is you start a Go routine and then you forget about it and it's waiting on some channel that never receives a message, and suddenly your memory usage goes up, but you don't really see what's going on. In the memory profiles, sometimes the Go routine profile can tell you that, oh my God, you're running 100,000 Go routines now. Maybe that wasn't what you wanted to do. One interesting feature of the Go routine profiler is also that it has a text output format, which can tell you for the Go routines that have not been scheduled in the last minute, so have been sitting around off CPU for more than a minute, it will tell you what they're currently waiting on, as in what the wait state is in the runtime internals, and how long they've been waiting as well. So if it's more than 1 minute, you'll see 1 minute, 2 minutes, 3 minutes, that sort of stuff, which can be super useful for debugging why a program is stuck or why you're leaking Go routines and stuff like this. Another interesting thing you can kind of build on top of the Go routine profiler is a walk log profiler, or I would probably call it more Go routine time profiler, but walk log profiling is what most of the industry calls it. And the way that can be implemented is by essentially taking a Go routine profile 100 times per second and then aggregating all the resulting stack traces. And I've got a little project on GitHub that does exactly that. But again, if you read the first bullet here, to do a Go routine profile, you have to stop all the Go routines and take a stack trace, and that's a stop the world operation. So doing that once might be okay, but if you do this 100 times per second, you can introduce serious latency into your application, which you probably don't want. So I wouldn't recommend this particular project for production usage. So bonus slides, we can talk a little bit more about Linux Perf and eBPF for profiling. So as mentioned before, Linux Perf works well with Go because it supports frame pointer, or Go supports frame pointers and dwarf tables. Perf can offer better accuracy than the built-in profiler, especially if you're still waiting for Go.1.18, then the perf results for spiky workloads will be closer to the truth. So that could be useful to know. Perf also nicely deals with edge cases like Go applications calling into C code, where by default, the Go runtime will not show you the stack traces for your C function calls or inside of your C code, unless you invoke a function called runtime set cgo traceback, which is a complex little thing, but people get it to work. But if you don't want to deal with this, perf just automatically gives you stack traces for your C code and for your Go code, because the frame pointers are easier to use for that particular stack unwinding. And really, there's only a few downsides to Linux Perf. The main thing is it's Linux only. So if you have a more exotic deployment environment, that could be a deal breaker. And security-wise, you usually need elevated permissions to run Linux Perf against a program. And you also don't get profiler labels. So if you want to attribute CPU time more granularly than stack traces, then you probably prefer Go's built-in tooling. And yeah, if you want to use Linux Perf as a Go application, it's really the same as for any other application. You just call perf record, give it a frequency for the interrupts, and then tell it to use dwarf or I think this was dwarf unwinding. No, sorry, I think it's just capturing stack traces. And then you call perf report to get the resulting profile. BPF can also be used to do profiling. Specifically, there's a few ways to do it, but BPF trace might be the most user-friendly BPF tool out there. And so one way you can use it is you can call BPF trace with this one-liner that basically just says run a profile at 99 Hertz and then capture a user stack trace and aggregate the number of times the same stack trace has been seen and output it. I think that by default just gives you program counters, so you still need to symbolize them. But it might require less context switching because stack trace aggregation is actually happening in the kernel. But yeah, otherwise similar caveats as the ones relevant to Linux Perf apply to this, namely security, profiler labels, all of that stuff. This brings us to the end of our presentation and a quick recap. Yeah, so basically Go is a bit odd for a compiled language, but it has a wide variety of profiling and observability tools available that can be used. Most of those should be safe for production, except perhaps the Go routine profiler and the execution tracer, and especially ureturn probes, which you probably never ever want to use with Go as things are right now. And yeah, continuous profiling is a great idea in this environment because you can basically get safe production profiles that you can always have at your fingertips. So I highly recommend looking into that. And if you want more in-depth information than this presentation on various profiling topics, I've got a GitHub repository called Go Profiler Notes, where I publish all my research and notes, and it has a guide that I'm working on and all kinds of in-depth information. So yeah, that's pretty much it. Thank you so much for your time. And I didn't see any questions in the chat so far, but if you have any, please bring them up now and I'd be happy to answer them.
We can stop broadcasting and we can invite everyone to approach you and to create circles so we can ask questions and discuss in a more fluid way.
Cool.
Okay, let's do it.
People trying to get used with the wonder.
Yeah, everyone's coming.
Yay, circle time.
Yeah. How large can a circle be?
15 people, I think.
Yeah.
From the demo I was looking at. So anybody has a question?
No.
No?
Still have to understand of the presentation. I cannot ask any question by now because it's a lot of information to process. So thank you very much.
Yeah. So maybe I can ask a question because I've listed some during your presentation. So I was surprised. I see the news about it, but I was very surprised to see that Go ABI, I mean the calling convention, was every parameters arguments on the stack. From if you look at the other languages, it's very unusual, I would say, to have that, even though in native, I mean on a native path. So can you elaborate more on the history of that choice and the way that they change it, and the way also that they trying to keep many convention in flight, I think, for the Go?
Yes. So the history is just that the people who created Go came from Plan 9, like Rob Pike and a few others had experience working on Plan 9, which was a Unix operating system that was, I think, developed by Bell Labs. And at Bell Labs, they did things a little differently than the rest of the industry. And they decided that it's easier to put all the arguments on the stack, because that makes it easier actually to support a large number of CPU architectures, because you don't need to do special stuff for different CPUs. It's just always on the stack. You know where it is. So there's something to be said for a simple elegance to that solution. But obviously, if you want to get really good performance, putting stuff on the stack is much slower than utilizing CPU registers directly. And surprisingly, Go got away with just copying the simple approach from Plan 9 for a rather long amount of time, and didn't look too bad in most benchmarks against languages that are competing in the same weight class. But yeah, obviously it was a not so ideal choice. And some of the applications that I heard that upgraded Go to 1.17 that were particularly perhaps making a lot of small function calls where that overhead shows a lot, they were seeing, I mean, I think the Go developers said 3 to 4% improvements are expected. Some people saw 10%, 20% improvements from changing the calling convention to register-based. So I think it's the right move, but it's always a trade-off. Another argument is to be made for frame pointers. A lot of languages omit frame pointers, which are basically a good way. Like when you call a function, what basically happens is you put the return address of that function on the stack. So you've got, when you get a stack trace, you basically just find all those return addresses. But in order to do that, you need to know the size of each stack frame to know where the return address is located. And the only way to know that is if you have debugging information such as 12, because otherwise you just look at the stack, it's a bunch of memory, and you don't know where those return addresses are. But if you know every frame frame size, you can find them, but you need debugging information. With frame pointers, you actually utilize a register called the base pointer register, which points to another place on the stack, which has a frame pointer, which points basically to the beginning of the current frame. And then that value found there is pointing to the next frame pointer that's also on the stack. But the downside to that is when you call a function, you don't just have to push the return address on the stack, you also have to push the frame pointer on the stack. And this instruction for doing that is not free. And in some cases can also be a couple percent of performance that it costs you, especially if you make a lot of small function calls that don't end up getting inlined. I think Go gets away with that particular design choice because inlining has gotten pretty good over the years, and they can inline a lot of stuff. But yeah, Go would probably run faster if we put frame pointers behind an option that you can enable or disable. And some people might like the extra performance, but then if you're trying to debug stuff in production and people don't put frame pointers in and strip the debugging symbols, then you can't do anything. You can't get stack traces anymore. You can't do profiling. And it sounds like people wouldn't do that, but you look at the container ecosystem and Docker people who try to make these really small images and strip everything from your binaries that they can possibly get strip out of them. And suddenly you end up with people using stuff like databases in production from some container image where maybe there's no frame pointers and there's no debugging symbols. And now you are between a rock and a hard place if you have a production issue. So I kind of admire Go's stance on that, saying, hey, we're going to keep the frame pointers, even if it makes some performance compromise, but it keeps stuff easier to debug in production. And also shipping debugging symbols by default in the binary, I think is a great choice.
Okay. I have a list of questions, so I can go on, but
Yeah.
if anybody want to jump,
Yeah, I'd like to jump in a bit.
yeah, go ahead.
Just one question, because I love the way you present things, Felix. Well, thanks for the presentation. But the way that you say, well, actually, it's not that expensive to have a debugging information and to do profiling in production. That's something with my different clients. I spend a lot of time saying, okay, you can invest a bit of performance to just get knowledge about what is happening instead of being blindfolded and just jump, do a phase jump into the production. So, and regarding everything you say, regarding the stance of Go, having the frame pointers and everything, do you think there is I would say an industry trend on saying that we need to get information and to be able to diagnose everything is going on in production? Or is it still something that is a bit particular on Go side, for instance?
I would say there's a big push in the industry to get more observability just as a result of the industry going crazy with complexity.
Okay.
And not just in the application themselves, like the systems we built that are distributed, and you used to make one request to an application that maybe makes a query to a database and then you get a response. Like that, those days are largely over for bigger companies, and you need crazy tooling to understand what's going on. And yeah, I think it goes from the sort of system perspective. Companies are working on products for like debugging systems down to, again, to the individual applications. BPF is probably the hottest thing out there right now, where people are trying to get really better observability and dynamic ways of debugging production applications. So I would say it's not limited to Go. I think the Linux people are very keen on this, and other communities probably as well.
Well, thank you. Very interesting. Thanks.
Yeah, to comment also on that, on the fact that we are trying to push to use the profiling in production and always on. That's a new trend basically in the industry. But the thing also, maybe people don't realize that distributed tracing is kind of accepted for everybody, and that's the baseline for that. But people don't realize that distributed tracing has also a significant overhead, and I would say if you're careful with profiling, sometimes profiling overhead is less than the distributed tracing overhead.
I would say that's probably common. I think distributed tracing overhead, logging overhead, instrumentation overhead is getting out of control in a lot of applications that I've looked at. Which isn't to say you shouldn't use those tools, but it's a trade-off.
Yeah, and the thing is, for me, profiling can get you more information than the different information, but for the quantity of information that you can get with profiling, instead of logging, or if it depends on how you log, and the distributed tracing can be very useful for you. So trying to consider profiling in production, it's a very good way also to have an observability system that is not so hungry about the overhead. Anyway.
I have one question maybe about the profiler overhead. I have some experience. I'm a bit skeptical about profiling in production because I have some bad experience in the past. So I wonder about the overhead you mentioned from 1 to 10%. Is it something that the profilers claim themselves, or is it something we can measure maybe with the go runtime, or it's something we need to measure by looking at our performance metrics on our side?
Yeah. I would say that the numbers that I've thrown out there are sort of ballpoint figures that come from experience of having run profilers on applications and done like a lot of isolated testing. I do want to get more disciplined about publishing some research on that, so we don't have to like take my word for it, and we can look at something and agree on that's a reasonable benchmark or not. It's very tricky though to measure things and to measure them correctly. I'd say there's two ways to think about the overhead. One is like from the measurement, you try to get the values. One is from first principles, you just think through what is actually happening when a sample is taken during profiling. So I like that approach because it gives us kind of a range of where we should end up with. And then if we see something totally different when we measure, that should give us pause. I'd say from first principles, what you need is, firstly, you need to interrupt the application somehow. That needs to happen. And well, there's various ways of doing that. For Go, it's signal-based. So you have to ask the kernel, if my process has spent more than 10 milliseconds of CPU time, please send a signal. And it turns out the accounting for how much time a process is spending on the CPU is running all the time anyway, because the scheduler in Linux needs to know how much CPU time stuff is spending, because it has to schedule applications and gives them access to the CPU relatively fairly. So back in the old days, the Linux scheduler, I think, had a Jiffy interval or something that was like 4 milliseconds. So basically every 4 milliseconds of CPU time, it was looking at an application thread and deciding should that thread get another 4 milliseconds or not. So you kind of had a switch from user space to the kernel space, a context switch every 4 milliseconds without profiling. Nowadays, my understanding is it's a little bit more dynamic, and the Linux kernel can decide to give a application more or less time on the CPU before it intervenes. I don't understand the details of that, but I would still assume that getting an interrupt on an application every 10 milliseconds is not that uncommon for just schedule purposes on a busy system that might not run a single process. Usually you have like sidecar stuff and agents and blah, blah, blah. So yeah, when you then ask for the interrupts or signals to be delivered when 10 milliseconds of CPU time are up, in the ideal case, the kernel doesn't have to do extra context switches. It basically just waits until it takes your CPU thread off the CPU and checks if it should get more CPU time or not. And if it notices that, hey, this CPU thread wants to be notified with a signal if it used a certain amount of time, then it can just go right back, schedule that thing back on the CPU and continue running it, just invoking the signal handler. But that is really not much more overhead than if it had immediately run back to the thread that was currently executing. So you're not really paying much extra context switching time, I think. But the context switching time would probably be a few microseconds. So I think it's 2 microseconds or something, 3 microseconds to do a context switch in Linux. So even if you do 100 of them per second, we're still only talking 300 microseconds of CPU time that are spent on context switching out of a million microseconds that we have available for that 1 second period. Then what happens in Go? When the signal handler gets involved, it has to take a stack trace. The stack trace implementation in Go doesn't actually use frame pointers, which would be faster. It uses its own asynchronous unwinding tables, which basically is giving information on how big the frames on the stack are. And then it basically knows where the where the return addresses are located without following the frame pointers. But that means it needs to load a lookup table onto memory. So that causes some memory thrashing. And it then needs to run some algorithm that is more complex than the frame pointer unwinding. But from my testing, to get a stack trace from an application that has a stack depth of maybe 16 functions currently executing, it's about a microsecond, maybe 2. So it's similar to the context switching time. And then basically once that stack trace has been taken, usually it gets put into a buffer that gets processed out of band for later on being converted to a pprof format, which also has some overhead, but it's not directly impacting the latency critical path because you can go right back and run your user code, and the pprof writing can happen in another thread. So overall, just from thinking through what's happening, it seems relatively low amounts of CPU time is being spent, relatively low extra context switching or stuff is going on. When you measure, you'll find that measuring stuff is very difficult because the results will depend on variables, specifically the stack depth. The deeper your stack, the longer the stack unwinding is going to take. Also, potentially the size of your stack frames could matter. If you have very wide stack sizes, and the cache lines that get hit when you load the return addresses could be much more, and you have to go through more memory and so on. So it's very difficult to agree on what a typical application would look like in terms of stack unwinding for CPU profiling. So I don't know, my attempts, I was doing stuff like making HTTP requests, but that's not a realistic workload, but just hammering an HTTP server with hello world requests. Other stuff I was doing is JSON parsing. And well, what I found is in most workloads, it was like 1% or 2 I could measure it, but it was pretty close to the noise floor level. But then I also found some interesting stuff. I found that for the HTTP benchmarks that I was running, I was able to make the Go application run faster by profiling it. So instead of slowing it down, it was running faster, not just a little bit. We're talking at a certain amount of Go routines. That was one of the variables I was adjusting because I found it interesting. It was going from maybe 1% or 2% of CPU overhead to suddenly being 30% faster. And then you're like, okay, if we're taking this measurement thing seriously, suddenly you have to debug all kinds of interesting phenomena, or otherwise just hide those results and push them under the carpet when you present them to the public. I was not able to get to the root cause. People have suggested stuff such as frequency scaling could be involved. Maybe that particular workload triggered some thermal or other thing, even though it was pretty reproducible on servers that weren't running for a long time. But yeah, there's all kinds of complex things that can be involved in that. But it also means that in reality, the overhead of profiling is the best way to determine it is to run your application, your workload with Profiler on and off, and having some good way to measure CPU consumption. And that will tell you what your overhead is. But I think most people will end up in the single-digit percentage range because it's now pretty common in the industry that people are continuously doing CPU profiling for their applications. So I would say you would hear more complaints if it was more than that value. I think 10% is sort of my mental threshold where I would say I would complain or people would start complaining. And we've certainly not seen that in the Go community. Memory profile, block profile, and mutex profile, those are all much lower overhead because they don't even have to talk to the operating system. They're just instrumentations in the runtime, and you can adjust the sampling rate. So basically, with the allocations, you only sample maybe 1 out of 1,000 allocations. With the block and mutex events, first of all, it depends on how many you have, but then you can set the threshold to some value that will make sure the overhead is not too high. Yeah.
Okay, thank you. And so 1-2% you mentioned that you got in your tests, that's something you got using your application metrics, not something that Go Runtime provides.
What I was doing specifically was measuring wall clock time, and I also recorded CPU time, both user space and kernel space for sanity. But basically, I had a Go program that was executing over and over again with and without profiling, and then measuring how long it took to execute, and got enough samples that I got some level of statistical confidence that I was not looking at random outliers.
Okay, thank you.
Okay, I can go on question. So when you use the CPU profiler from Go, you cannot profile the GC time, for example. You can see only the Go routines, right?
Yes. Well, you can see how much CPU time is used by the GC because it's possible to interrupt the Go process while it's currently running some GC-related operation, and that will show up as runtime mark object sweep something in the CPU flame graph. That doesn't show you latency, that shows you CPU time. Most of Go's garbage collectors now running very nicely in the background, and the amount of time anything ever gets stopped is now, I think they're in the tens of microseconds now in stop the warp time. So I think it's competitive with Java for the purpose of GC latency, but in terms of GC overhead and CPU costs, you can see that on the CPU profiler. You can see the latency. They have a ring buffer where they put recent garbage collector stop the world pause times, and you can read out stuff out of this ring buffer and put it into some time series or whatever you have for monitoring.
Okay.
Any other questions?
I saw also an article about the issue with the set I timer, but there is a proposal about using PMU events instead.
Yeah.
So can you comment on this one?
Yeah. So Uber, the company, they had somebody working on Go profiling. I think they were unhappy with the accuracy of the profiles. I don't know how much of their unhappiness was we actually couldn't debug the issues we had versus we hired some PhD person who's really good and smart and wants to push it to the next level. That was a little unclear, but you can make the accuracy of the Go CPU profiler look really bad. So there are workloads right now that you can throw at it where it's totally off. But in production, it turns out that most people seem to find that the values you get out of Go's profiler close enough to Linux perf that it's usable and you can solve real issues with it. Yeah, for the PMU events, hardware events, what they were doing, I think, is one, I think they were allowing you to have the interrupts fire based on different events. So the Go CPU profiler is just using CPU time, which they supported as well. But you could also fire a interrupt after a given number of instructions. And you could fire it after a given number of cache misses or cache hits in the L1, 2, whatever caches. That's probably very expert level profiling features. And it would have required to make the API of Go profiling more complicated. And the Go developers were not too interested in it because these features would only ever work on Linux, where you get access to those APIs for, from what I understand, the other operating systems didn't have interfaces or some sort of stuff. At least the patch that Uber provided was only Linux. And so the Go guys were like, we're not going to introduce a huge API for profiling crazy stuff just for Linux. And also I mean, the other concern is you have to keep the other profiler around because you can't just suddenly say profiling is a Linux only feature. So you have to keep two relatively complex implementations around. Doing this sort of profiling where you interrupt the program and then you make sense out of where you got stopped is not trivial. So a lot of parts of the Go runtime, like the garbage collector, etc., have to be aware of what's going on, and maintaining two subsystems that would go at this from very different angles is gnarly. So I think it's a great idea to get better profiling and accuracy, but I think in the real world, if you really, really care, you can use Linux perf. You can wait for Go 1.18, which will make it significantly better. And maybe we'll get a chance to study this in sort of a competition where we throw some workloads at it again and see how well Go's new profiler does versus Linux perf. But yeah, no, I think it's a great effort that the Uber guys made, but then they were unhappy that the upstream guys at Go didn't want to merge their patch. And so they announced their project essentially as a fork of Go. And I think they called it Prof Plus, or I forgot what they called it, but it was kind of a passive aggressive move saying like, hey, you're not merging our patch, so we're publishing our fork of Go now, which sometimes that works and it kicks something into gear and the upstream guys decide based on the trauma that results, they'll merge it. I think in this case it hasn't happened. But yeah, people who are willing to compile their applications with Uber's version of Go can do it and get better profiling. So it's nice to see interest in pushing that forward for sure.
It does. Okay, I can. For me, that's enough.
Okay, this was fun. Thank you so much for having me, and
yeah, sure.
Everybody's having a nice evening. And
yes, thank you so much.
Felix, thank you so much.
Thanks, Felix. It was great. Cheers.
Thank you. Bye.
Bye.
Thank you.